We have reached the last section of the course. In section 7.4, we're going to be looking at applications and modeling with these radical functions that we've been talking about. And we'll start by finding square root models to fit data. As always, we look at a specific type or a specific format for our models. And the format we're going to be using for our square root models is this one right here. A times the square root of x plus b. So first of all, if I only have 2 points, I can actually find these models by hand. First of all, I'd like to find a model of this form that contains points 0, 6 and 4, 12. If I have the y-intercept is once again just going to be the b value. I'll show you that here, although we can use that as a shortcut later on as well. If I were to actually plug in the point 0, 6, so 0 for y or f of x, 6 for y or f of x, and then the 0 for the x. A times 0 is just 0, so I simply have the b equals 6 over here. So I now have f of x or y equals a square root of x, and I now know that the b is 6. We'll just go ahead and plug in our other point now, 12 for y, and 4 for x. That gives me 2a plus 6. Subtracting the 6 is equal to 2a, and so a would be equal to 3. I know both a and b, so I now know my model. The function 3 square root x plus 6 would be a square root function that contains both of those points. All right, let's try one more. This time, again, I have 2 points, but I don't have the y-intercept this time. So I'm going to start the same way as before. I'm just going to plug both of those points in. Keep in mind, my model is always going to start with a square root x plus b. And I'll plug in this first point. Y is 7, and x is 1. So I just get 7 equals a plus b. Unlike when I had the y-intercept, that doesn't give me enough information to solve for either a or b yet. So let's plug in our second point. This time y is 11, and x is 9. So 11 would be 3a plus b. And again, a perfectly good equation, but it doesn't give me the information I need to solve for either a or b quite yet. If, however, I put these two equations together, I now have a system of equations, 2 equations and 2 unknowns. And if you think all the way back to our very first unit, or actually I guess it was unit 2, when we were working with linear functions, we solved systems of equations like this. We had a couple of different methods, right? We had both a substitution method and an elimination method. Either one works. I'm just going to go ahead and use elimination. It's not too difficult to get the b's to cancel out. I would just need to multiply one of the equations by -1. I'm going to choose this first one. So I'm going to multiply both sides by -1. It's going to make this -7 equals minus a minus b. Second equation, I'll just leave the way it is. And now if I add my equations, notice how the b's will be eliminated. So I have 4 equal to 2a, and therefore a is equal to 2. If a is 2, I could plug that back, say, into this equation. It doesn't matter, by the way, which one you use. I now know a is 2. So that's going to give me 5 for b. So I know both a and b. That means that my function is my a, 2, square root x, plus my b is 5. All right, what if we have more than just 2 points? As we've seen before, if we have data, it may not precisely fit a specific model, but it might indicate by the shape of the data that it's close to a specific model, in which case we can use regression with well, actually with Desmos. This is one thing our calculator will not do, but Desmos definitely does. We could use Desmos to model the function from the data. So go ahead here and let's see. We're going to go ahead and make a scatter plot and find a square root model for this data. So for each of these years, we're told how many viewers of the American Idol TV show there were. And I'm going to go ahead and let 2002 be represented by t equals 0. So this would be 0, 1, 2, 3, and 4. I will say that especially with square root models, there's a definite advantage in letting the first year correspond to 0. I rarely make any other choice with square root models. If you think back to our modeling type, you'll notice we incorporated a vertical shift and a vertical stretch, but we didn't add or subtract anything to the x inside the radical. What that means is we have not incorporated any horizontal shift, and as a result, I really would like to start my data in the year 0, not shifted to the left or right from that. All right, so let's go ahead and I'm going to grab Desmos and I'm going to put this data in. And let's take a look at it. All right, if you look at that data, a square root model isn't a bad choice. Now I'm going to mention, I also see the possibility maybe of a cubic model here. So I wouldn't argue with anyone who said a cubic model isn't a bad choice either. Sometimes when I get into that point, I start asking myself the question, what do I think is going to happen from here? If you visualize a square root model, right, it keeps going up, but it keeps going up slowly. Do I think that American Idol became suddenly way more popular after this point, and all of a sudden the viewership went up drastically? Or do I think instead that the growth seems to be slowing down and maybe it's just going to keep on growing but slowly? I think it's more likely to go slowly than really, really fast. And so for that reason, I'm visualizing more of a square root model, which grows slowly, than a cubic model that would grow quickly. All right. We can look at them both, but I'm going to start with the square root model. Y1 in our regression, so tilde. And then I'm just going to type in my square root model. A times the square root of x1 plus b. Notice the r squared is 0.99, so it's a really good fit. I can see visually it looks like a good fit, and you can see how that grows really slowly. Before we quit, I just want to show you what would happen if I tried a cubic model, because I wouldn't deny the shape indicates that it might be a good choice. You can see the fit's really good. In fact, the r squared is even a little bit better than the radical. But this is where I think the square root model is more realistic. You can see the cubic model starts to go up very fast. And realistically, I don't think that's really what happened with viewership for American Idol. It may have continued to go up, but I think it went up more slowly. It didn't suddenly go up more quickly. So this is a case where, despite the fact that the r squared is actually a little bit closer to 1, I still don't think the model is as realistic as the square root model. And those are the kinds of choices you'll be needing to make in the final project as well. All right, so let's go ahead and write down our model. Let's see, I'm going to call A the number of American Idol viewers, and T is going to be my T values here for the years. And so A of T is going to be, let's see, the little a value according to Desmos is about 8.846 times, we usually say square root x, but in this case square root t for my input variable, plus the b value, again going to Desmos, 12.246. Right. This is to use the model to predict when the number of viewers will reach 38 million. So put A of t as 38. And I'm going to go ahead and solve this one by hand, and then we'll go ahead and check it with technology this time. So to solve by hand, I'd have to subtract the 12.246. And that's 25.754. Then I'll divide by the 8.846. I get about 2.911. Goodness, I don't know where that 6 all of a sudden came from, square root t. And then finally we'll square both sides to get rid of the square root, right? That's the inverse function. And I have about 8.5 for t. Since 2002 was my starting year, that's a little more than 8 years later, so that would bring us to sometime during the year 2010. Alternatively, let's see, I'm going to get rid of this cubic model that we decided not to go with. Alternatively, I could have simply added the, what was it, y equals 38 to my graph, and I could have solved it with technology by looking right there where they intersect. And again, it's about 8.5, so that just sort of verifies the answer that I got by hand. All right, the last question here was to predict the number of viewers for 2007. Again, my starting year was 2002. So that would be a t-value of 5. And if I just plug that into my function and find a of 5, I get about 32.03. And that was viewers in millions, so about 32 million would be our prediction for 2007. All right, we have another application here for our radicals. I know you've all, I'm sure, used a Pythagorean theorem before. Basically, it just says that if we have a right triangle, so a triangle with a 90-degree angle, right? 90-degree angle, a perfectly square corner right there. A and B are the lengths of what we call the legs, the shorter sides. And C is the length of the hypotenuse or longest side. Then it will always be true that A squared plus B squared equals C squared. We'll make use of that to calculate a missing side. If we're given any two, if we're given any two sides of a right triangle, we can calculate the value of the third side by using that Pythagorean theorem. So in our first example, we have values for A and B, but we're missing the value for C. So when I set up my Pythagorean theorem, I'll have A, or 8 squared, plus B, 5 square root 5 squared, and that's going to equal the C squared, and I'm going to work at solving for C. 8 squared is 64. I can apply that square to both factors here. So 5 squared is 25, multiplied by the square root of 5 squared, which would just be 5, right? Inverses there, equals C squared. 64 plus 25 times 5 is 189. And then to solve for C, really I just need to take the square root of both sides. Just as a reminder, typically when we take square roots as part of our equation solving process, we always say, hey, we got to take into account both the positive and negative square roots. Here, since C is the length of the side of a triangle, it doesn't really make sense to take the negative square root. So I'm going to say realistically, we want to keep just the positive answer in this particular case. And I don't think that comes out evenly, but I could break it down, simplify that radical. Let's see, 189, I can see that 9 goes in there 21 times. So the simplified form of my answer would be 3 times the square root of 21. All right, let's try another one. This time I don't know the value of A. B is 9, and C is 11. So my equation would look like A squared plus 9 squared equals 11 squared. So A squared plus 81 equals 121. And to solve for A, I'll subtract the 81. And then we'll take the square root on both sides. Again, technically when I solve, I should take into account both the positive and negative square roots. But realistically, I know the length of a side has to be positive. So I'll keep that positive again. And can we break that radical down and simplify it? A perfect square that goes into 40 would just be 4. So 4 times 10. And we'll say that the a value this side is 2 times the square root of 10. All right, I have a couple more. These last two don't have numerical values for the given sides. They have some variables already in them. And so instead of getting a numerical value for the third side, what I'll end up getting is an expression that contains an x or contains an a for my third side. So in this problem, I have a is 4, b is x, and c is our unknown. So my equation would be 4 squared plus x squared equals c squared. That's 16 plus x squared equals c squared. And to solve for c, I'd take the square root on both sides. I'm just going to go ahead, we've seen this a couple times now, and say, hey, length of a side has to be positive. So we'll stick with just the positive square root here. And so c is the square root. A reminder, you cannot take the square root of a sum by taking the square root of the terms separately. That is not the same thing as 4 plus x. So for c, the simplified form of my answer has to stay as the square root of 16 plus x squared. All right, one more. This time, I'm using the letter A here as my part of my problem, so maybe I'll just label my sides with capital letters. I'll call this A, B, and C. So my Pythagorean theorem would just be capital A squared plus B squared equals C squared. So I'd have 3A squared plus 4A squared equals C squared. That would be 9A squared plus 16A squared equals C squared. And those are like terms, I can go ahead and add them up. 25A squared equals C squared. To solve for C, I'll take the square root of both sides. Again, length of a side has to be positive. And this time I can simplify, right? I can't take the square root, when there's addition, I can't take the square root of the pieces separately. But with multiplication between the factors here, I can. So that's just 5A. So C is equal to 5A. All right, we have one more application to finish out this section. It's called the distance formula. And it allows us to calculate the straight line distance between any 2 points. So if I have 2 points, x1, y1, and x2, y2, and I want to know how far apart they are, I'm trying to calculate the straight line distance between them. The value of d, that distance, is given by this formula. The square root of x2 minus x1 squared plus y2 minus y1 squared. Notice again, these terms are added, So I cannot simplify this. I can't take the square root of the term separately. I'm stuck with this. All right, let's go ahead and calculate a distance using that formula. In our example, we want the distance between 2, 1 and 6, 4. So 2, 1 and 6, 4. And that is the distance that I'm trying to find. According to my distance formula, I start by taking x2 minus x1, so 6 minus 2. Plus y2 minus y1, that would be 4 minus 1. Square that. So that would be 4 squared plus 3 squared. Square root of 16 plus 9, which is the square root of 25. So that distance in this case is just 5. A quick little aside here, distance formula looks absolutely great and nothing wrong with just using it. But what I wanted to point out to you is that this formula really shouldn't surprise us. If you think about that straight line distance between the points as the hypotenuse of a right triangle, notice that the base here of the triangle is 1, 2, 3, 4, and the height is 1, 2, 3. And so I could have written 4 squared plus 3 squared equals d squared. Oops. 4 squared plus 3 squared equals d squared as the Pythagorean theorem. Then when I take the square root of both sides, I would have ended up right here with the square root of 4 squared plus 3 squared, and it all would have looked the same. So in actuality, the distance formula is really just another statement of the Pythagorean theorem, is all it is. Just a fancy way of showing it. All right. Our last problem. Given these 3 points, it says to show that the triangle ABC is a right triangle by showing that it satisfies the Pythagorean theorem. So let's graph first and just see what we're looking at here. A is negative 2, 1. B is 2, 3. C is 3, 1. So here's the triangle I'm looking at. And you'll notice that if it's really a right triangle, the only angle that could possibly be the right angle would be that one right there, right? So we're going to try and show that that's a right triangle, hopefully with a right angle here at B. Now I'm going to draw it in there, but I'm going to kind of right now say, is it really a right angle? We can't tell just by looking at it. Looks like it could be, but of course we need to show that. So what I'm going to do is I'm going to calculate the lengths of the 3 sides, and if I can show that those 3 lengths satisfy the Pythagorean theorem, then I'll know for sure it has to be a right triangle. Only right triangles satisfy the Pythagorean theorem. So let's go ahead and I'm going to call my sides A, B, and C, anticipating that this would be the hypotenuse if it's going to work. And I need to calculate the lengths of those 3 sides. So I'm going to start with little a. Little a is the distance between A and B. So if I think about my 2 points here, A and B, and I put those into my distance formula, I'd have the square root of, and just a reminder, subtract the x's, square that, and subtract the y's and square that, right? So 2 minus negative 2 for the x's, squared, plus 3 minus 1, squared for the y's, is 2 minus negative 2, that would be 4 squared, plus 2 squared, 16 plus 4 would give me the square root of 20. Now, I don't necessarily need to bother simplifying that. I could if I wanted to, but my goal isn't really just to find the lengths of the sides. My goal is to show that we have a right triangle. And I don't need simplified forms to do that, so I was going to leave that one. All right, B. B is the distance between point B and point C. So once again, I'm going to use my distance formula. X's would be 3 minus 2. Square that. Plus the y's would be 1 minus 3. Square that. Square root of 1 squared plus negative 2 squared. 1 plus 4 would be the square root of 5 for B. All right, C. C, I can take a shortcut. C is just a horizontal distance, so while I could use the distance formula, it's a lot more work than I really need to go through, right? I can count this one. 1, 2, 3, 4, 5. Just counting 5 units. All right, to show this is a right triangle, I need to prove that a squared plus b squared equals c squared. A is the square root of 20. B is the square root of 5. And C is 5. So squaring the square root just gives me 20. Again, here squaring a square root, that just gives me 5. And of course 5 squared is 25. And that is absolutely true. So since the Pythagorean theorem worked, I know this must be a right triangle. All right, that brings us to the end of the section and the end of the course.